Welcome back. So this will be the part 2 of this chapter, this series on coupled oscillation. In the first part, we looked at a specific case of 3 springs and 2 masses. And then we saw how we can use Newton's equation to find an oscillatory information. Now, in most cases, the problem is more general. We work in 3D. We have many more masses. So we are going to build this general formalism for the coupled oscillation, and then we will use it for a number of examples in the subsequent screencast. Okay, so the effect of coupling of two systems with 2 degrees of freedom leads to the characteristic frequencies that we have seen. So what happens in general case? So we are going to suppose in this case that we have a conservative system for which we will use generalized coordinates qk. So the generalized coordinate, of course, the one that we encountered already in the Lagrange formalism, and of course time is a parameter that we use for the differential equation. We will suppose we have n degrees of freedom, and actually an important requirement is that we suppose that we have a stable equilibrium. So in other words, the system can be found in a stable equilibrium state. And we will note those as qk0, 0 being basically the equilibrium. Now we can write the Lagrange equations, but in particular we can certainly write the Lagrange equation for the initial condition, and we know that they are going to be satisfied for the system that's stable, since we decided that it exists. And of course, the stable situation is described by qk equal qk0 as by notation. The velocity is 0 for all generalized coordinate, and of course the acceleration as well, since it's at equilibrium. So let's have a look a little bit more about what's happening here. So we know that though all the non-zero term of the time derivative of the derivative of the Lagrangian with respect to the generalized velocity will contain only either the velocity or the acceleration. That's the usual trick that we use in Lagrangian mechanics. So that means that in our case, we know that if we calculate the derivative, of course, that means that the time derivative is 0 for the stable situation. That means that according to the Lagrange equation, the derivative of L with respect to qk at equilibrium, that's what the vertical bar with 0 means, is equal to 0, and of course L is equal to t minus u, and we can write this very easily. So that's a very important result, a very straightforward result maybe, but it's a result that we are going to use, which means that the derivative of the kinetic energy with respect to the position to the generalized coordinates at equilibrium 0, but also they are equal to du over dqk. Good. We're also going to make an assumption that we have used also in the past to derive a number of equations, which means that the formulation to go from the generalized coordinate to the Cartesian coordinates, or the rectangular coordinates, do not depend on time explicitly. So there is no time dependence in these transformations. That's not always the case in Lagrangian mechanics, but in the case of the study of vibration, this is the case in this particular context. We saw in the chapter on Lagrange mechanics that if that is the case, then the kinetic energy can always be written the way I just put on the slide here, which is simply a quadratic form, a generalized quadratic form of the generalized velocities. Okay, so that's not a big surprise. I mean, this is a formula that you recognize if you were using the Cartesian coordinates. This is sum of mv squared over 2. Here we also have cross term that j and k because we are using generalized coordinates. When we'll see example, it will become very clear to you. Okay, but so what we see here is, of course, the kinetic energy does not depend on the positions. Therefore, we can write that the derivative of t with respect to the position is 0, since there is no dependence. And if you remember the previous slide, we knew that the derivative of t with respect to qk at 0 was equal to the derivative of u with respect to qk at 0. Therefore, since that one is 0, we also find at equilibrium the potential is minimal. Again, it's a result that you have used before in fundamental physics courses, introductory physics courses, that the potential is zero. The potential is a minimum, sorry, at equilibrium. That's not a big surprise, as you remember. If the potential is conservative, the du over dqk is related to the force, and of course minus the force, and of course there is no force at equilibrium. So there's nothing really surprising here. But we would like to do this clear, to make this very clear, because well, we will use that result in a couple of slides to have a general result for the formalism. We will also suppose that the potential is actually zero at equilibrium. That's, as you know, the potential can always be, the reference for the potential can always be picked artificially, if you will, I mean arbitrarily. So we can use, for example, that the minimum is at zero. That's not really an issue. That doesn't remove any generality of our theory here. So the question that we usually ask when we get to this point, where we are looking at what happens around the minimum, the question we always ask ourselves is what's this physicist's best friend? Well, and you know, the best friend of physicists is, one of the best friends is Taylor series. I mean, you can say that another good friend is Fourier transform and things like this. But in our case, Taylor series are our friends because we know, we have characterized what happens in the system at equilibrium. And now we want to know what happens when we deviate slightly from equilibrium. Okay, this is really the context in which we want to work. So we are going to use Taylor series for the potential. The potential only depends on the coordinates, q1, q2, and so on, all the way to qn. And of course, the Taylor series up to second order is given by the formula that you see on the screen. The dot at the end are the third order, fourth order, and so on and so forth. As you know, the series continues forever. Okay. Now, there is something very important to notice, is that the first two terms actually vanish. Okay, the reason why the first term vanish is for the reason I gave you about 45 seconds ago, that the potential can be chosen to be zero at equilibrium. And the reason why the second term vanishes is I just also explained to you a couple of minutes ago that the derivative of the potential at equilibrium with respect to the coordinates is also zero, right? Not surprising. So that allows us to say that a good a fairly good second order approximation for the potential around the minimum is the quadratic term. So in other words, can be written like this. This is a very important result that you are going to use a lot, actually. The fact that the potential is a quadratic, formula of a quadratic description of the potential. And what you just heard on the screencast is just Siri on my watch that decided to help us, but it was not very helpful, so I turned it off. And so the potential is given by this formula, and the coefficients a, j, k are just the second derivative of u with respect to the coordinates. So this is the Hessian of the potential. So that's very nice. Now, is that always a good approximation? Most of the time it is. When the qk's are small enough, the third order become very, very small. And so the third order is like something that would be qi times qj times qk. They're very small. So usually we turn them off. And this is called the harmonic approximation. Okay, so this is good. Now let's have a look. So we have this, and we know that if the potential is the second derivative of the potential are continuous, calculus tells us that the Hessian is symmetric. So that's an important thing. Now we also know that u has to be positive. Why should it be positive? Well, because we said that the minimum was at zero. So if we say that the minimum is at zero, of course, every other value is larger than zero, so they're positive. So that's good. We also know that the kinetic energy is always zero, is always larger than zero. That's very clear as well, okay? Because these are quadratic terms in the velocity, we know this. So, what have we done so far? Well, we've done two things that are very useful. First one is that we could write the kinetic energy in the first equation. That was only true because the relationship between the generalized coordinate and the Cartesian coordinates that does not depend on time. And the second term is because we would like u we use the first non-zero term in the Taylor series of u around the equilibrium. So that's very nice. Now, we should spend a couple more minutes on the m's, on the mjk. So the m forms a tensor. We have the formula for mjk. This formula was also obtained in the chapter in the Lagrangian. In the Lagrangian mechanics. Let's have a look a little bit here. We are also going to write the mjk using Taylor series, and you're going to understand why we do this. So the mjk will be, if we want to find a Taylor series around the minimum, they will be obtained by this formula, where I actually stop after the first order. I didn't go to the second order. Now, the problem with this equation here is that neither the mjk at QL0 or the derivative are 0. So that's just a fact. They are not 0 because there is no reason why they should be 0, in fact. And it turns out that the first non-vanishing term is actually the constant. So now it turns out that what we need to do is to actually, in order to have a good approximation, and this is actually a little bit of a subtle point that I'm going to try to explain, in order to have a good approximation, we can drop all the terms above the constant. The reason for this is, if you remember, when we looked at the potential energy, we used a second order approximation in the Q's, right? It was a quadratic term. So since we are making an approximation on the mjk, we also need to do an approximation of the same order. Otherwise, we are mixing. We are more accurate in one term than the other, and this is a recipe for disaster. So we need to stay on the same order of accuracy. And it turns out that the t already depends quadratically on the q's, right? It's q dot j, q dot k. So that means that if we want to stay in second order in the coordinates, we also need to use a 0th order in the mjk. So that's the reason why we need to do this. So I hope this is very clear. If it's not, I suggest that you rewind 20 seconds and listen to this again. So we end up having m's, which are just terms without worrying about the derivatives. And we usually obtain them by comparing to the kinetic energy that we can calculate using physics, I should say, as we should do in any physics course. Again, this is going to become clear when we look at examples. Okay. Imagine now we have two tensors, A's and the tensor with the elements of AJK and the tensor MJK. If we could find a way to diagonalize those two tensors, at the same time, there would be no cross term. Remember, I'm going to go back one slide, maybe a couple of slides like this one. If you look at these two expressions for t and u, if the mjk and ajk were diagonal, there will be no term where the two indices j and k would be different, right? If only the j equal k terms will remain. In other words, we would not mix the different coordinates. In other words, we would decouple the system. So we would decouple the coordinate, the generalized coordinate. So this is usually something we like to do, and we are going to discuss a lot about that in the rest of the series, that we would like to actually find a way to decouple the contribution of the generalized coordinate for the kinetic energy and also so this is true for t, we can write it this way, and it's also true for u as well. So this is basically saying that they are only the diagonal term, and we do not mix. That would be great if we could do this, and in fact, there is a formalism that allows us to do that, and we will do this in this series later, which is called the normal coordinates. So the normal coordinates are actually those special cues that make m and a diagonal. Okay, so this is something that we are going to use a lot. So these are now the equations we have. So remember, these two equations are actually approximations. They are quadratic approximation. We understand that we could write them because we drop all the higher order. But this is what we use. And now those equations look really like equations that we could solve, and this is what we're going to do. But before we do that, let's try to see which equation we have to solve. And of course, as you know, when you know the kinetic energy and the potential energy, you can calculate the Lagrangian as t minus u. And so the Lagrangian, the equations of motion can be obtained from the Lagrangian L using this Lagrangian formula, which hopefully by this stage of the course should be no surprise. Now, we also know that the L is equal to t plus t minus u, but the only piece that depends on qk is u, and the only piece that depends on q dot k is t. So in other words, we can rewrite that equation this way. By the way, the minus became a plus because L is equal to u minus t, right? T minus u minus t, yes. It doesn't matter in this case since it's equal to 0. Okay, wonderful. So what does that mean? That means that the only thing that we need to calculate now are the derivative of the potential energy with respect to qk and the derivative of the kinetic energy with respect to q dot k. So that's what we have right here, right? It's very straightforward to do the derivative of the form that are shown on the top left quadrant of my slide. And so when you put everything back together, you find that the equation of motions are written this way. So the first time you see these equations, it may come a little bit weird and you may wonder what we are doing. But it's actually, the derivation for them is actually not that complicated. I think it took me about 7 minutes to do that. It should take you about the same time. So the point is, once we have we find a way to calculate the coefficients ajk and mjk, which I gave you the formula for, then we can solve those equations. Now, one thing that's always a little bit more difficult for students, and that's what I'm going to try to explain here. This is one equation here on the top, in the title of this slide, where we do a sum over j, right? But this equation depends on k, and in fact, k goes from 1 to n, right? There are n. This is the size of a and the size of m, basically. And it turns out that we can write that equation for each different value of k's going from 1 to n. So in other words, we have n differential equations, right? So we have n differential equations. So if it is a little bit complicated for you, just go back to the first part of this series, where we actually had 2 equations, and we wrote them explicitly, and so we had 2 equations to find 2 solutions. And again, we're interested in oscillatory solutions, so we are going to write them this way now. This is slightly different notation than what we used in the first part of the screencast, but it's because we wanted to use aj to be real. And if aj is real, we can put the phase into the e to the power minus I delta. This is just a property of complex numbers that you know it's pretty elementary complex number. Okay, so this is really nice. Now, we want to try those solutions that we are going to inject in the equation, and we hope that the frequency will be real. Okay, the frequency should be real. Actually, it's not a hope. Because of the fact that we are working close to the minimum, the frequency should be the omega square should be positive. This can be traced back to the fact that we have positive definite equations. We are not going to go there, but it turns out that if omega square is positive, the frequency themselves, the square root, will be a real number. So, and in fact, if it were not real, that means that you would have an exponential decay, and that's a decay, an exponential decay of the amplitude, of course, means that you are losing energy, and if you're losing energy, that means that you're in a damped situation. Therefore, you would not have conservative forces in that case. But remember, one of the constraints we impose at the beginning of this formalism is to say that the potential is conservative. So there is conservation of energy. Therefore, we do expect the frequency. We do know that the frequency will be real. But again, we are going to inject this solution, this oscillatory solution, into the differential equation. And as a result, we obtain, again, equations that look very much similar than before, but the difference now is that these equations are actually algebraic. And the algebraic equations for the AJ. Again, these equations are just a generalization of the two equations we found for the case of the two masses and three springs. And we have a series of equations. In fact, we have n equations of this shape. And the n equation come from by changing the index k. And once again, if we have a system of algebraic equation, n equation, those equations will be compatible if the determinant is equal to 0. And they are going to be equal to 0. This is a way we note this. And this is usually called the characteristic or secular equation. And actually, it's useful to write it explicitly for a large system, and it would actually look like this. So the determinant you would have to calculate looks like this. And the number of rows and column will be equal to the number of degrees of freedom we have. So again, if we want to go back to the example that we looked at the beginning, in the part 1 of this screencast, we had two equations only. Okay. So solving this determinant will allow us to find the omega square. We were going to find n possible value of omega square for this polynomial of order n. And this is going to be called the eigenfrequencies, and they correspond to eigenvectors. So this is really, really, I would say, pretty simple once you have mastered the notations, really. I mean, this is the equation. And we are going to review this in a summary, and then we are also going to cover a few examples to try to cement this understanding. But before we go there, let's talk a little bit about the coordinates. So far we spoke about the frequencies. It turns out that the general solution in this kind of linear problem, if we have n solution, the general solution is actually a superposition of all the possible solutions. So what we've done so far is to calculate the specific solution AJR e to the power I omega RT minus delta R. And we found n of those. And those n, we are just labeling them with the index R. So R goes from 1 to n. And it turns out that any linear superposition of those coefficients, of those solutions, is going to be a solution as well. So this is the general solution we have. Of course, we do not forget that the solution is actually only the real part. We are using complex numbers, but because it's very easy to deal with exponential. But in this kind of theoretical physics, we do not need complex number. In fact, complex number don't mean anything in the experimentally. Instead, it's the real part, which is, of course, the cosine part of the exponential using Euler's equation for the EI omega t formula. So this is really nice. So we see that of any motion, so a motion is a trajectory described by QJT, is going to be a compounded of motions at different frequencies. So that's basically what it means. It's a decomposition of the motion is going to be, any motion can be decomposed as a linear combination of the frequencies, of the eigenfrequencies of the problem. And those eigenfrequencies are obtained by solving for the determinant as I just described to you. So this is actually nice. So of course, as I said before, our life would be easier with normal coordinates, because normal coordinates means that all the matrices will be diagonal. But patience is a virtue, and we will have a look at that in a later part of this series. Okay, now it's time to go back to the problem we started with, which is again this problem that we solve using Newton's equation. We are now going to try to see if we can solve it using what we just did now. Well, for that we used to calculate the potential energy. Remember, we need to find the coefficients AJK, which are the second derivative of the potential energy. So in order to calculate the derivative, we need to calculate the potential first. So the potential energy, well, it's actually much easier than the force because we don't have to worry about the signs. It's going to be simply the energy in the first spring, the second spring, and the third spring. This is what we obtain. And we can write this, we can actually decompose this using the usual formula. and we obtain these terms. I'd like to attract your attention that the coupling between the coordinates is pretty obvious here. This is the coupling right here. Okay. By the way, this potential is actually second order, right? So the approximation that I mentioned to you, that we actually stopping the Taylor series at the second order. Actually, in this case, the approximation is exact because there is no third order term in these coordinates. Now, once we have the potential energy, we calculate the A's. Remember, the A's are the Hessian of A. So we have 4 of them, right? These are the 4 elements of them. So what I suggest you do at this point is to pause the screencast and try to calculate them for yourself. And then what happens is once you do this, you find that the second derivative of A with respect of U with respect to x1 squared is kappa plus kappa 1, 2, and so on and so forth for the other terms. I will notice again that here we have 2 degrees of freedom, so we have 4 coefficients A's, but we only need 3 because A12 is equal to A21. Okay, so that's all good. And if you're not convinced, just calculate A12 and A2 and you will see these are the same value, of course. Excellent. So of course the second part, as you know, when you do Lagrangian by now, should be a reflex for you. You have to look at the kinetic energy. Kinetic energy is also written pretty straightforwardly, knowing the velocities. And we see that if we compare this to the equation that we have for T, which was the 1/2 sum over mjk qj dot qk dot, we see directly in this case that the m's that correspond to this, okay, using this equation here, the m's that correspond to this is m11 equal to m1, m22 equal m, and there is no cross term, there's no dynamical coupling as we call it. So dynamical coupling is a couplings that involve the velocities of 2 particles at the same time. Here there is no such thing, so if there is no dynamic coupling, like for example x1 dot x2 dot times x2 dot, the off-diagonal terms are 0. Excellent. And then of course we can calculate the circular equation by using the formula that we use with AJK, MJK, and we obtain this determinant. And actually we can stop here because that determinant was exactly the determinant that we found in the first part of this series. So of course everything that follows will be the same. So that's it for this part. I mean, this is the complete theory. In fact, we are going to continue studying this a little bit to do a little bit more theoretical description in the next on the third part, and then we are going to apply this to more and more systems. Thank you very much for your attention.